All right. So welcome everybody to Alex. I'm going to mess up his name, even though I already asked. Eftimiades, his talk on testing machine learning models in production. So Alex, I'm going to stop sharing and let you share.
Okay, sounds good. Welcome everyone.
Oh, let me do the bio while you're sharing, because I almost forgot that too. See? Focused on other things. So Alex is a data scientist at FINRA, working jointly between the Quality Assurance Department and another group within technology that researches anomalies that may be indicative of insider trading and fraudulent activity. So he applies machine learning and statistics to address these areas. Alex originally studied physics and is passionate about applying math to solve real world problems. He previously worked as a data engineer and a software engineer. So basically Alex is like a caped crusader, but he uses data to do it.
Sure, I'll take that.
Sure, yeah, take that compliment. Yeah, yeah. So now you can wear a cape, it's fine.
All right, we're in business. So I'm gonna be talking about some of the results and some things that we've learned since the days of conducting some R&D on how to monitor and test machine learning models in production at FINRA. So FINRA, as we've noted, kind of looks for financial crimes, and they look for a number of different financial crimes. I work for one particular department, and I also work within the Quality Assurance Department. And I kind of juggle responsibilities between the two. And we did some, last year we did some R&D on how to monitor and test machine learning models, and since then we've tried to put a lot of these initiatives into production. Since monitoring machine learning models is in some sense a superset of kind of assuring them, for the most part, there's some disjointness too. We're going to break it up into two parts where we go over kind of how we'd assure machine learning models in general, and then go on to some of the initiatives we've kind of undergone with regards to monitoring machine learning models. So just a quick kind of pros and cons, or discrepancy T-chart here. Traditional software requires you to have like a business rule in mind that you're going to implement using code. Like something comes in, maybe it's a number and a string comes out, or you validate that it's that you're looking at a valid credit card number or something like that. You have expected outputs. You would test it with expected outputs for given example inputs. And if it doesn't give you the expected output, it's a bug because the test failed. That's all well and good. And frankly, traditional software like that is really good for most problems. The problems where you don't necessarily know what the rule is ahead of time, but you just have examples of it, or where machine learning kind of becomes useful. So it's kind of the stuff that traditional software engineering practices aren't very good at. For instance, recognizing a face or recognizing a certain trading pattern that might be indicative of some sort of financial crime in our case. We have examples of what analysts have gone over years and identified as potentially suspicious or not, but we still don't have rules, hard set rules for what to look for ahead of time. So you could train an algorithm that tries to learn those rules given examples, and the output of the model might be some sort of a confidence on a scale from 0 to 1 of how likely this would be labeled as suspicious behavior, for example, in our case, or how likely something is a cat as opposed to a dog for image classification. And a single wrong prediction, or maybe it being very not, so going back, you would take those scores and you would probably threshold them at some point to say, this is a decision or this is going to be a decision. So if it's above a certain confidence, we will consider this suspicious for the purposes of flagging somebody's attention. Now, a wrong prediction isn't necessarily a bug. We're looking to maximize performance as measured by some sort of an average of how right the model is. We might use different performance metrics, as we'll see, for different purposes, but a single wrong prediction isn't a bug in this case. And generally, you would assess model quality as a function of how accurate it is according to your performance metrics. And again, those are specific to the use case you have in mind. Now, most of the software in a machine learning system isn't actually machine learning. Most of it is kind of data engineering and data plumbing that transforms data from maybe a SQL table into a data frame, and combines several data frames, and then turns them into can be transformed to the columns and sends them into your model. So that's to transform the inputs from their sources into something that the model actually expects to receive. And then takes the output and maybe does some post-processing to that to turn it into a nice chart. For example, we might have a series of orders, which are somebody placed a buy order at this time for this many shares of this ticker symbol at this price. And we have a series of orders like that, which you might transform into daily opening, closing, high, low prices for a symbol on a given day. And yeah, so that would be something that that's just an example of standard data engineering, and you would test that with standard software practices. You would use unit tests or what have you for testing those, which is fine. But there's sort of an added layer on top where we want to know whether the data we used to, let's say, train the model was representative of everything the model was going to see in production. And generally the answer is no, but you could sort of think about it with some domain expertise and figure out whether it's a good, what you've used as training data is a good approximation for what the model will see in the wild. For example, if we were training a model that recognized some sort of a trading pattern and we used only trades from the month of January 2020 that may or may not be relevant a year later because trading patterns change, might depend on what the model's purpose is. So to help mitigate to help figure out whether this was done well, we would usually use a separate holdout set, say the month of February, to determine whether the model still has learned something that carries over to things that it hasn't seen before. And in doing so, we can learn whether the model is overfit. For example, if hypothetically everybody who made a profit in January did so on a Tuesday, that would almost certainly not carry over to subsequent months. It's just a coincidence. But if maybe day of the week was a feature in your model, that could be something that the model picked up inaccurately, but it could be something that it overfit on. So you could validate it on February's data to see whether it was still just as accurate. And typically the performance will drop because in practice, almost all models are overfit to some degree or another. So it's not the end of the world, but you will generally see a performance drop between the training and the validation data. And as a consequence, you'll know the degree to which it's overfit. And the idea is that when you validate on February's data, or maybe a month later, or a year later, or whatever, you still have a reasonable idea of that'll give you a reasonable idea of how well the model is going to do in production, because it wasn't related to the training data. So one of the other things that we've actually found, I found at least one bug in a machine learning system with this technique, is looking into feature importance. The idea is that if you can interpret your features, if let's say they're opening and closing prices for something like that, and you have some meaning attached to them, like the pixels on a screen for image classification aren't necessarily terribly interpretable, but those prices I mentioned are. We have meanings associated with those. We can use a notion of feature importance, assuming that we have one in mind regarding the degree to which these features should influence the model output. So for instance, I worked on a project in which some features were supposed to increase the model score. Increasing the value of some of these features should generally be considered to increase the likelihood that that person was committing some sort of fraudulent activity. So with respect to that notion of feature importance, we used correlation to correlate the feature with the output of the model for a whole bunch of examples to see whether those particular features did in fact positively correlate with the model output score. And there's a whole lot of different notions of feature importance floating around, and a lot of sophisticated open source implementations of them. One of the things that we've learned from looking into a lot of these was that they tend to correlate in practice. So using these different notions of feature importance often in practice gives similar results, but they have very, very specific interpretations to them that may or may not correspond to what you're actually looking for when you're trying to use feature importance as a kind of sanity check. Does increasing this feature actually increase the output of the model score? If, for example, that's something that you should be seeing. So it's just something to keep in mind. When you're looking for feature importance, keep in mind what you're actually looking for by feature importance, and use a measurement that corresponds to that concept you have in mind. So moving on to actually how we quantify performance. At FINRA, as I mentioned, a lot of our applications are along the lines of find suspicious activity and separate it from the noise, from most activity, which is not suspicious. And to do that, RockAuck, something known as RockAuck, which is series of two acronyms for receiver operating characteristics, area under the curve, is a very common and useful performance metric that we use for this case. So Brockach of 1 would mean that if we were to sort the output, if the model was to be run on a whole bunch of instances and spit out numbers between 0 and 1, saying 0 being this is 100% certain that they're not doing anything suspicious, and 1 being 100% certain they are doing something suspicious, a Brockach of 1 would have everybody who is potentially doing something suspicious at the top of the list. So if you went from the top to the bottom, you'd find everybody who is suspicious, and then you would just be left with noise. That's the ideal situation. Brockach of 0 would be the opposite. Everybody who would be labeled as suspicious in practice is at the bottom of your list. And a 0.5 would be if they're evenly distributed throughout the non-suspicious people. So it's no better than a coin. And the downside to this kind of thing, while it's a very useful way to measure model performance for binary classification, like what we do at FINRA, is that you need somebody to actually go over and check whether these people were actually doing something suspicious or not. You need a human to come in and determine whether something was actually awry, which of course defeats the purpose of the model. If you're going to check whether everybody was doing something suspicious or not, why do you need a model in the first place? You're going to have a human do all the work. So that's kind of a trade-off there. You have to determine what proportion of these predictions you're actually going to check. So as for monitoring, to a first approximation, monitoring is validation over time. So we're going to look at, for instance, the Brockach over time. We could wait a month. Maybe we could wait a week, and we'll get 10 new labels, let's say, and we'll compute a Brockach and say for this week the model was this accurate, and we can do the same thing for next week and next week. Or we could wait longer and maybe wait a month and say this is the Brockach for this month, and this is how well the model did over this month, and see how it does over time. And in general, we're looking for situations where the performance is unacceptably low, in which case we might flag an alert and say, hey, is something wrong, or have trading patterns changed, or is there a bug in code somewhere that's surfaced now? But there's kind of a trade-off in terms of how long you want to wait for data to come, for labels to come in, as analysts actually go over these labels and figure out whether they're correct or not, and how fast you can react to something going wrong. So if you do this, for instance, every day, it's kind of bebopping around all over the place, as you'll see in that last graph, and it'll get gradually smoother as you wait longer. Well, why is that? Well, let's say, for instance, we were measuring performance with accuracy. Accuracy is usually regarded as the percentage of the time that the model's right. If you threshold the output and say anything above the score is suspicious, everything below it is not suspicious, and let's compare that to whether they were actually suspicious or not suspicious. So what percentage of the time was the model right? Now, you wouldn't actually use that a lot in practice, because if 99% of the time they're not suspicious, then a model that just says everybody's not suspicious is 99% accurate. Not very meaningful. But for the sake of simplicity, let's say the model is either right or it isn't. So over the course of time, we measure how right it is. And let's say that we get one label a day. Well, let's say we get like 4 labels a day. And we do this every day. And we find out the model was 100% correct on Monday. We got 4 of 4 correct. Well, that's kind of like flipping a coin and getting 4 heads and saying that it's 100% biased in favor of heads. And then the next day you flip it 4 more times and you say it's 100% biased in favor of tails because it came up tails all the time. Those kind of average, you'll get a better sense of how biased it is if you wait longer and flip it more times. If you flipped it 100 times, you're probably going to get something between like 48 and 52 heads. So that's why there's this kind of trade-off here. But we have this other technique we can use called divergences, where we can't necessarily know that the model's bad, but we can at least say that the data going into it has changed with respect to the data that the model was trained on. So going back to that January-February discrepancy, was the training data and the validation data similar, or were they different? That's something that you could potentially use that for too. But the idea is, was January's data similar to February's data? Or if we wait 10 years from now, was that month's data similar to the January data that we trained the model on? We developed some internal tools that, fingers crossed, will hopefully be maybe we might be able to open source in the not too distant future that measure how different two different distributions are. There's other systems out there. I'm fond of the one that we developed. It was computationally cheap to execute and doesn't depend on the number of samples. And the reason was because regardless of whether you're comparing a billion trades on let's say January and a billion trades on Wednesday, you don't need all billion to figure out whether those two Excel sheets, for example, are significantly different. In practice, you need like on the order of 10,000, and that's fine. So if you downsample from whatever you have to whatever you need, you're always fine. So I'm going to try to illustrate how we go about doing this with two examples. The first is called Earth Movers distance, and let's imagine we're trying to compare price and volume in January to price and volume in February. Volume being the number of shares that an order asked for. So we take all the orders in January and we make a scatter plot in terms of price and the number of shares they wanted. And we have the scatter plot here, and let's say January's in red. And we do the same thing for February, shown in blue. Now let's imagine, bear with me, that January's orders were piles of dirt, and February's orders, the blue, were holes in the ground. And all the piles of dirt had the same volume, and all the holes in the ground had the same volume. The total amount of dirt in the piles was equal to the total amount of dirt missing in the holes. So we got piles of dirt in red, holes in the ground in blue. And let's imagine that we put a little worker at each of those piles of dirt with a shovel and had them coordinate in the most efficient way possible to shovel the dirt into the holes with the least number of steps between them. That least number of steps is called Earth Movers distance, and it's a really useful way to quantify how different two different distributions are. And the neat thing about it is we don't have to write down, we don't have to like try to fit curves or do anything like that. We can just take two Excel sheets and run an algorithm. There's a bunch of open source implementations of this that run in about cubic time that determine how different two different distributions are using this technique. So that's really cool. The problem is it's not scale invariant. Well, what does that mean? Well, let's say we're looking at penny stocks, and the price is typically like on the order of cents, so like $0.1, something like that. And because they're so cheap, people are placing placing orders for lots and lots of shares, maybe on the order of hundreds of shares. So on maybe on the y-axis where there's price, we're looking on a scale from 0 to like 0.1, maybe $1, something like that, if it really spikes. And on the x-axis, we're looking at on a scale from 0 to like 100, 1,000, something like that. So those steps that those workers are taking are mostly going along the volume direction because the plot's so stretched out like that. So any discrepancies in price movements are basically lost using this measurement. So for the purposes of using kind of a black box model like this, we would generally prefer something that's scale invariant. And there's a class of measurements that we could use that are scale invariant called F-divergence, of which there's a particularly interpretable one called total variation shown with this plot on the right. Now, if we imagine we were just looking at price for a second, and we look at January's prices in blue and February's prices in red, and we try to fit a curve to the histogram of prices we took in January and February to make these little bell curves here. One half of this gray region between them is our quantity that measures how different they are. And that turns out to vary between 0 and 1, with 0 being they're right on top of each other, there's no gray to show, and 1 being they're like infinitely far apart and they're totally different. And this generalizes to multiple dimensions. So if, let's say, there was a big discrepancy in price on the first graph, divergence of 0.789, and a little divergence, very little discrepancy in volume, we could do both at the same time and kind of measure the gray volume between the two plots. And we would get something that's generally at least as big as the divergence for any one feature. So this change kind of compounds as we add more features. We don't generally get the divergence for multiple features is at least as great as the divergence for any one of them, at least for total variation, as you can show here. So that's something that we kind of keep in mind. But so we can use it across all the features to see whether there's something wrong, and then we can narrow it down to individual features to see if any one of them is wrong, or maybe any combination of them is wrong. So we actually tested this last year on some real data that we had in the company. And we, for instance, there was a model floating around that was trained on July 25th, and we calculated the divergence between the training data and the data taken for each of these other days of the month of July. And you can see they floated kind of high, around from like 0.3 to 0.4. So on a scale from 0 to 1, that's kind of high. So we tried to figure out what was going on there. So we compared every day to every other day in the plot shown on the right in these crosstabs here. And you can see it's 0 along the diagonal because we're just comparing that day to itself. And typically days are within like 0.1 total variation of each other, maybe a little bit less, except for July 25th. That was like on the order of 0.4, 0.44 compared to every other day. So it was much more different to other days than other days were to each other. And it turns out that there was a bug in the data pipeline that day. They were missing a feed that went into their went into their pipeline that they kind of upstream. So they had feeds from multiple exchanges, and one of the feeds from one of the exchanges just wasn't working that day. So all the unit tests passed. The prices were reasonable; they weren't negative or anything. All the volumes were integers, but the distributions were off. So you think, oh wow, we can use this for everything, right? Not quite. So if a single price went negative or something like that, you're not going to catch that if there's several million orders floating around that are all perfectly fine. You need large shifts for this to show up. Like if maybe all the prices were multiplied by a factor of 10 because your units were wrong, that could show up, but not onesie twosie kind of changes just don't show up this way. So you think, oh man, well, that's not very useful, is it? Well, there's some subtle cases where this can capture something that you wouldn't get with unit tests. For example, let's say the buy-sell code was flipped. Everything that was a buy got labeled as a sell, and everything that was a sell got labeled as a buy. So the buy-sell code seem reasonable. In fact, the proportions of buys and sells seem pretty reasonable because they're typically a 50-50 split anyway. The prices are all ballpark about right. The volume for the number of shares that they're requesting is all ballpark about right. So how could we tell the difference? Well, people like to buy low and they like to sell high. In fact, most orders don't go through for this reason. People are buying too low and they're selling too high. And the few times where somebody places a buy that's above somebody's sell, the exchange keeps the difference and the order goes through. So if the buy-sell code got flipped, everybody would be buying high and selling low, and you'd be able to see a big shift in the distribution of prices. So that's kind of a cool scenario that we'd be able to catch with this technique that we wouldn't be able to otherwise. So at this point, I'm going to move on to thresholding in the time that remains. So let's say we want to set a threshold to trigger an alert. Now, this could be as the result of a model saying a score, outputting a score on a scale from 0 to 1 according to how confident it is that something's suspicious, or it could be we're thresholding the performance of the model over the course of a month and saying that anything below this threshold is worth investigating further. Or maybe we're thresholding the divergence that we measured with respect to the training data and saying any deviation above this amount is worth investigating. Well, in any case, we still need to decide on a threshold and determine where to put it. Now, again, if this measurement we were using was a perfect separator of things that go wrong from things that don't go wrong, or suspicious things from non-suspicious things, it would be pretty obvious that we would just put the threshold at whatever point we start to see bad alerts generated and say anything above that, let's look at that only and don't look at anything below it where we start getting bad alerts. But of course, nothing's perfect like that. And there's going to be some trade-off in terms of the amount of noise that you're willing to withstand to keep getting good alerts that might be further down this list. So if, for example, we have this historical data here, and we find that generally performance above 0.8 or performance below 0.8, it generates a good alert in the sense that there is something wrong with that model. So we say, okay, we're going to threshold it at 0.8. 6 months later, maybe something went wrong and the performance was 0.84. We missed it because our threshold was at 0.8. So there's this kind of trade-off here. We don't necessarily know where to put the threshold. And generally, we could put the threshold at 0 and get everything if, let's say, we're going to look at things above that threshold, for example. If we put the threshold at 0, then we're going to get everything. And that's not ideal, because then there's no point in setting up this monitoring system in the first place. We're just going to investigate everything. So you have to make some sort of a decision in terms of how many false alarms are worth getting a true alert. how much time are you willing to waste with these false alarms to get the next good alert? And maybe you have the decision that you're willing to waste two false positives for one true positives, two bad alerts for one good alert. And that would influence your decision on where to put your threshold. So you might start at 0 just to start seeing where the good alerts are and where the bad alerts are. And then you might move it up as you learn more about how they're distributed, and you might eventually settle it on some place in the middle that gives you that optimum trade-off between true positives and noise. So at any given point, you're kind of left with two decisions. You don't apply a threshold just for the sake of labeling things, so you can get an idea of where the good alerts are on the spectrum, or you could apply your threshold and try to make the best use you can of the information you have, but you won't find out what's below it. So there's this trade-off here. So as part of this R&D project, I helped to develop this algorithm that tries to balance the opportunity cost from not using a threshold and probably wasting time in doing so, but in exchange, getting some new information about how to optimally put it, or where to optimally put it the next time around. So it'll try to balance that opportunity cost of doing that, of just making a measurement and having people label things for the sake of labeling things, with the utility gained over subsequent rounds from the new information. So we told them just label this for the sake of labeling it. Let's not threshold, shown on the left. We'll get some new information about where to put it the next time around. And the next time around, we moved it a little bit, and we were able to satisfy our needs a little bit better and get a little bit better trade-off from positives and negatives, false alarms and good alerts. And over subsequent rounds, we'll eventually make up for that opportunity cost in using that new information. And at such point that we do, we say, okay, good enough, let's take a new measurement and have them label something again. And the neat thing about this is over time, we're going to tell them to just label things for the sake of labeling things less and less, because we're going to get a clearer and clearer picture of where to put those thresholds. And in doing so, we're going to gain less and less from telling them just to label things. So it's going to take more and more rounds to make up for that opportunity cost. Therefore, we're going to tell people to label things less and less on average, if that kind of makes sense. So over here, I generated some fake data. We have this distribution of good alerts, and let's say they're typically high. So anything above that threshold is going to be considered an alert, and typically larger scores, larger values correspond to more likely to be a good alert. So we have our positive alerts that are distributed like this, and the negative alerts are kind of distributed like this. And as you can see, there's no particular place that's going to separate them perfectly. But let's say that we decide that four false alarms are worth one good alert, and that corresponds to or implies a utility function that looks like this middle plot over here. And you can see there's probably the peak of the utility function, or optimum place to put a threshold, is probably around 0.6. And there's this little bit of a shaded region here that corresponds to our uncertainty in this utility function itself, because we don't have an infinite amount of data here. I actually only generated 3,600 rounds, which was a lot, but it's not an infinite amount. And this shaded region shows there's a 50% chance of the utility function falling within that region. So if we had maybe 36 rounds as opposed to 3,600 rounds, this would be a huge error bar. But because there's a lot of labeled data here, the error bar was quite tight. However, in practice, we would not want to wait for 3,600 performance measures, 3,600 months to go by, for example, if we're doing this on a monthly basis, to find out where to put our threshold. We would want to start setting thresholds sooner rather than later. So again, using all of this hindsight, 3,600 rounds worth of hindsight, we have a kind of uncertainty spread of where to put that optimum threshold. That is the peak in this utility function shown in the center graph, with this blue curve over here. So this blue curve on the far right shows where we think we should put our optimum threshold given 3,600 rounds of hindsight. And it's a pretty sharp spike around 0.6, because we're pretty sure that the peak of this utility function is around 0.6. Meanwhile, in practice, we would probably be exploiting our knowledge of where to put that threshold much sooner than 3,600 rounds later. We would be using these green thresholds down here, which the algorithm has been generating in real time. So the idea is, you can see epoch increase. You see the little epoch number at the within the title of that third plot increasing. That's the number of rounds that has transpired so far. And you can see it starts out near the when the epoch is low, with a very broad range of thresholds it's using because it has no idea where to put them. But over time, it asks for feedback more and more often, and it learns to figure out where the optimum place to put the thresholds are. And those little green ticks for thresholds that it chooses tend to cluster around 0.6 over time. And you can see the green curve kind of starts to peak around 0.6 as well, in that vicinity. So last slide, the question we could ask is how much time is wasted in doing this? How much time did people spend just labeling things for the sake of labeling to understand where to put their threshold over time? And the answer is about 10% over the course of these 3,600 rounds. It starts out at about 45% because it doesn't know where to put anything at all. And it's as soon as you tell somebody to label something for the sake of labeling something, you gain a wealth of information about where to put the threshold, and it doesn't take long to make up for that opportunity cost. So it keeps telling people to just label something. I need to know where to put the thresholds. But over time, those thresholds kind of hone in on that 0.6 mark, and it asks people, it takes longer and longer to make up for that opportunity cost because it's making smaller and smaller adjustments to that threshold. And it drops pretty quickly to around 0.5 at the end. So that was kind of how it balances what we would call in reinforcement learning, exploration with telling people to just label something so we can learn about the system, with exploitation. Let's set a threshold so that we can make use of your time as best we can. So with that, I'll turn the talk back to for questions.
Yeah. So if anybody has questions, let's start with some green cards. You can put them in the chat, or you can just hold them up. All right, go ahead, Curtis.
Okay. When you're judging financial transactions like this, like I imagine that when you're trying to measure how accurate your model was, like how do you know when it's a good time to take that measurement? Like I don't imagine that you instantly know whether a transaction turned out to be fraudulent or not, like in reality. So how do you know when you've waited long enough for the data to come back and like, yes, these transactions were actually fraudulent and we flagged them or didn't flag them?
So in our case, and I think in a lot of cases in practice, a human makes that call ultimately. So in our case, we would wait for, if we flag an alert that says that somebody did something suspicious, maybe they committed some financial crime, or we think they might have. That means that an analyst actually has to go cyberstalk them and figure out whether they were doing something wrong or not. And we get that label a long time later. Now, there are, to be fair, some earlier stages in the pipeline where an analyst might just look at their trading patterns at a kind of a high numerical level with an Excel sheet or 3 or 10. And they'll say, yeah, this is worth passing on to somebody who's actually going to cyberstalk them. So we can also work at that higher level in the pipeline and get feedback much faster, and often do. So yeah, that's kind of when we find out whether somebody has to like label them in a UI, which then goes into a backend, and we can pull it later. You could imagine this also working for like weather prediction, where it's really obvious how you know in hindsight whether you were right or wrong.
Yeah, whether like you can tell pretty definitively, well, like 10 days later, right? Because that's as long.
Yeah, it depends on.
But financial transactions, like I know I'm not very involved in the stock market, but I know I have like 30 days to flag something on my credit card statement, right? And I imagine that it's something similar to that. They have, some amount of time to flag things as fraudulent, and the FBI or SEC has some time to investigate the transactions and throw people in jail right before they decide. And then there's courts and stuff. Is like, was this actually fraud or whatnot? So it seems like there could be a long tail to that, and I was just wondering how you manage that. So thank you.
Yeah, again, in practice, we look at the earlier stages in this pipeline for quicker feedback, but we don't know for sure whether it's going to pan out in a quarter or anything.
Makes sense.
Any other green cards? Since we don't have any current threads. Curtis, you got another one? Go ahead.
If nobody else does, yeah. One of your slides said new information is biased and not to be used to adjust threshold. I don't understand what new information is biased means.
Fair enough. Yeah, so if you set a threshold and only investigate things above it, that with a score that comes in above it, you don't know what fell below it, but you did investigate stuff that, let's say if you set your threshold at 80%, anything that came in with at least 80% confidence. So in principle, you could use that to adjust your threshold and figure out where to put it the next time around. And you didn't have to tell them just to label something for the sake of labeling something without, you could still use the information you gleaned from setting the threshold. The problem is it gives you a really distorted picture of where those good alerts and the bad alerts are. Oh, hang on, I don't want to share that. Can I share? If I can just share. Well, that's the short answer. I'd like to go back to just share the PowerPoint, but I seem to only have the option to share what's the screen in front of me. I'll see if I can work on that. But yeah, the short answer is it gives you a distorted view of where those good alerts and bad alerts are because you're only looking at the ones that come in above the 80%.
All right, next, Eric had a green card.
Okay, my experience with testing against machine learning models usually has to do with testing the adjacent systems. So a lot of testing in that sort of circumstance where there's, in that sort of circumstance treats the system processing those algorithms as a black box. So I have to think about things in terms of proving that the interface I'm building around the output of these continues to work correctly. I was wondering if you had any experiences or feedback you would share about treating these systems as and mocking these systems so that we can write automation against systems that are running these libraries.
Yeah. So, going back to the point I made earlier in the talk, a single wrong prediction isn't wrong. Now you could test that the model hasn't changed in the sense that it's literally the same file that you uploaded it after training. And you could, let's say, test that with a single input and a single output and make sure that the output matches the expected value. But that doesn't tell you anything that hashing the pickle file that represents your model couldn't tell you anyway. Like if, let's say, you serialized your model into an object that was imported into your pipeline later, you could just hash that file itself and see whether that's changed. So there's not much you can say in terms of comparing outputs to expected outputs that can't be said just by saying that, oh no, the model is literally the same file we uploaded during training. Nobody's tampered with it. There isn't much you can say in that regard. Now you can say that the accuracy has changed or performance is with regards to some performance metric. That's what we were talking about with regards to monitoring performance over time. And you can say if the performance is below a certain threshold, it might be suspicious or there might be something wrong and worth investigating. Does that kind of answer your question? You mentioned interpretability too. I wasn't sure if you had something regarding that I might have missed.
I mean, I can just start picking your brain for 6 more minutes if there are other people on the stack though. Is there a name for that technique of reusing a same baseline data set? I've proposed this before and didn't seem to quite be communicating with data scientists I was talking to about the concept of if I give the system similar inputs, I should at least get somewhat expected outputs or something that looks sane to me.
If you give it similar, oh yeah, that was the concept or at least I was hoping to communicate with these kind of divergences here. The idea is that did the data change significantly? Even if it's not the exact same data, did it at least seem like it came from the same source? So if, for example, going over here, let's say let's say we just had a model that looked at prices. And here are prices from Tuesday, and red is prices from Wednesday. We can quantify how different they are using this measure over here that shows what's the area between the two curves. And a zero area would mean that the curves are right on top of each other. It's literally the same data set. And one would mean that those curves were moved infinitely far apart. And that can generalize to higher dimensions too. The caveat being that you have to compare, you have to have kind of numerical features for this to work. There's caveats with categorical features that makes this less practical, not impossible to apply. And typically, if you want to apply this technique yourself, you can build histograms and just take the difference between the average difference between the bins for Tuesday's histogram and Wednesday's histogram. We have some other techniques that we built into this internal library that I worked on at FINRA that, fingers crossed, again, hopefully we'll open source in the not too distant future. That'll work much more efficiently with these. But that's the idea here. The general term is divergence for in statistics, and total variation is an example of a divergence that has some nice properties. It makes it easy to interpret.
All right. Any other green cards? I don't have anything else on the stack. Eric, if you have more questions, we have about 3 more minutes.
No, I'm out of my depth at this point.
Okay.
Going back to that question about why we can't use the information to be gleaned after thresholding, you're gleaning what you're looking at. This is the plot I wanted to pull up. If let's say you threshold at 0.8. This is your new distribution of positives, and 0.8 down here, this is your new distribution of negatives. It's very different from what the actual total distribution of positives and negatives are. So if you just look at stuff above the threshold, you don't get an accurate idea of where everything is throughout the entire range of possibilities. So that's why you can't use that information. And I've tried to make use of it, and it doesn't work nearly as well as just not using it at all.